Good morning, everyone, and welcome to 40 years at the interplay of information theory, probability, and statistical learning, a workshop honoring Andrew Barron. I am Joe Chang, James A. Atwood Professor of Statistics and Data Science at Yale and Chair of the Department of Statistics and Data Science. It's a thrill to see so many familiar and new faces here today from locations spanning 4 continents. And we appreciate all the efforts everyone has made to come together here. I want to express my deepest gratitude to all our distinguished speakers and everyone here in attendance. It has been a pleasure to work with the organizing committee, including Dan Spielman and Emily Howe from the Institute for the Foundations of Data Science, former students of Andrew's who have illustrious careers of their own, Bertrand Clark from University of Nebraska, Yuhong Yang from University of Minnesota, Cindy Rush from Columbia, Feng Liang from University of Illinois, and current student Curtis McDonald from Yale, and operations manager of the Statistics and Data Science Department, Matt Dutkowitz. Thanks also to event staff, Mandy Singer, and again, of course, to Emily Howe. We are grateful to conference sponsors, including the Institute for the Foundations of Data Science, the Departments of Statistics and Data Science, Computer Science, and Columbia Statistics Department and the National Science Foundation. Today, we gather to celebrate the remarkable career and contributions of Andrew Barron to the fields of probability, information theory, and statistical learning. For 40 years, Andrew's pioneering work has not only advanced these fields individually, but also demonstrated their interconnectedness and synergies, fostering a vibrant community of scholars exploring these fundamental ideas, as can be seen from the group gathered here today. The fields of information theory and statistical learning are the lenses through which we view the limits and the potential of inference. They teach us to distinguish what is possible from what is not and how to turn the possible into the real. Speaking on a personal note, I have a special appreciation for Andrew's impact, not only academically, but also on my own career. I was an assistant professor here when Andrew joined us from the University of Illinois as a full professor. At the time, Yale had no tenure track, and the statistics department was using all of its allocated faculty slots. And obtaining the additional slot required for my promotion to a tenured position even to be considered was seemingly not possible. Maybe it was his information theory instincts. In any case, Andrew conjectured that it was possible. And he provided a proof one semester when he was acting department chair and was able to secure that additional slot. The next semester, he worked with Department Chair David Pollard and John Hartigan to put together the tenure case. I had taken a position at UC Santa Cruz in the meantime while all this was going on, and I was considering staying there. One day, Andrew visited the university, eagerly hosted by David Hausler and Manfred Warmuth, and at one point, Andrew turned to me and said, "This is a great place, but Yale is better." His conviction and efforts played a pivotal role in my return to Yale, to the pleasure of working with Andrew for these decades, and the opportunity to be here with you today. Next, it is a pleasure and privilege to introduce Tamar Gendler, Dean of the Yale Faculty of Arts and Sciences, Vincent J. Scully Professor of Philosophy, and Professor of Psychology and Cognitive Science, not to mention Yale College graduate with majors in humanities and mathematics and philosophy. Dean Gendler has been a steadfast and enthusiastic supporter of statistics and data science at Yale and a wonderful friend of the department. I have found that her presence uplifts every meeting, and I'm so glad that she is able to be here to share her perspectives to open this conference. Please join me in welcoming Dean Tamar Gendler.
It's really an incredible honor for me to be here celebrating Andrew Barron and celebrating the room whose intellectual focus he has shaped. You will notice that there are not a lot of empty seats in this space, and you will notice that this is not a small space. This is completely unsurprising. Andrew Barron is, I like to think, a man of multiples. Many of our faculty, for example, serve in an administrative role. They might be chair of their department or director of undergraduate studies, or they might serve on a committee. Andrew Barron not only chaired statistics and data science, he was director of undergraduate studies in statistics, in applied math. He was the director of graduate studies for statistics for so long that it changed his name before he could step out of the position. He is a person who does everything that he does with multiple energy. So I had the pleasure of looking through your CV in anticipation of today's event. And one of the things that touched me most was that you include on your CV the fact that you are a 1977 graduate of W.T. Woodson High School in Fairfax, Virginia. But I don't think it's accidental to list early beginnings when you look at somebody like Andrew Barron. From the very earliest days of his career, his outstanding mind was evident to the world. He won in 1990 the Best Paper Prize for all IEE journals, the Browder J. Thompson Memorial Prize for Authors Under 30, which is meant to indicate future promise, sometimes realized, sometimes not. In this case, realized in multiple. As one goes through the CV of Professor Barron, it becomes evident that he not only opens up new horizons, he opens up new places to imagine horizons being. It is no accident, I think, that he is an individual whose avocation involves soaring above the earth, seeing that which others cannot see. I want to read to you some words that I read on the occasion of Professor Barron's retirement, because they so carefully articulate the ways in which he is special. Andrew Barron, BS, Rice University, PhD, Stanford University, faculty member at Yale since 1992. You are a trained electrical engineer who is also a statistician and whose research spans, it doesn't say this, but like the wings of a glider, whose research spans areas of mathematics, probability, statistics, information theory, engineering. Applications of your work are far-reaching and range from information theoretic aspects of portfolio estimation in finance to theoretical understanding of neural networks. The breadth of your learning means that your research has been able to build bridges across these disciplines, showing that together they have more in common than is often accepted or assumed. Each discipline is stronger as the result of your work. When I am describing what is special about Yale University to those whose application of information theoretic aspects of portfolio information whose application of information theoretic aspects of portfolio estimation in finance have allowed them to benefit therefrom, and whose inclinations have led them to share that goodness with the university, what I say to them is, Yale is special because its work has deep roots which enable broad branches. By deep roots, I mean that we understand things at Yale more foundationally, more profoundly, at a more principled and fundamental level than most other institutions, and that because of that, we are able to support broad branching work. Ordinarily, when I am making that case, I am making that case so as to encourage somebody who's interested in broad branches also to help us with our work in deep foundations, or vice versa. It is very rare to have an individual who is the whole tree, whose roots go so deep that they bring us to levels more fundamental in our understanding than we realized it was possible for us to reach, and the application of whose work are so patently evident, not over a time course of millennia or centuries or even decades, but over a time course of years and months and weeks and days. You are a person, Andrew Barron, who connects us not just intellectually across disciplines in the abstract, but in the fundamental endeavors of the university, that of understanding the nature of the universe and applying that understanding so that things which seem disparate, neuroscience and finance, come to seem tractable in a way that was heretofore not understood. It is no accident that when I met you first, it was in a small, charming building on Lower Hill House, and that when I greet you today, it is in the crowning space that serves as an organizational visual space on campus for all of our disciplines. Andrew Barron, thank you for uplifting us literally and metaphorically and helping us to soar along with you.
Thank you so much. Yeah, you've captured very well the spirit that I like to have, that, in these data science fields, we come from disciplines, people from computer science, from mathematics, from electrical engineering, from statistics. John Tukey described the role of statisticians at their best as being able to play in the sandboxes of all their friends. And, I don't think this group of scholars that you'll be hearing from in these next 2.5 days need any convincing of the value of this interplay in the sandbox that has statistics and information theory and probability. We may be at this triangle of these three topics a little bit more towards one or the other, but everyone you'll be hearing from values this interconnection. And that's what we're trying to champion here. I think I would like briefly to mention some roots. So I studied at Rice. You'll hear from others who have Rice connections. Don Johnson, Sid Burris are examples of influences from there. But even more at Stanford, from the electrical engineering department, my advisor, Tom Cover, Abbas El-Gamal, Bob Gray. From statistics, with Percy Diaconis and Brad Efron and Ian Johnstone. These were people that very much influenced me as I transitioned into a research career. And they also, from even way back then, there was already at Stanford a strong overlap. I went to Tom not knowing the value of statistics for the things that interested me. But as he learned of my interest, he said, go take as much probability in statistics as I could. And so that's something I tell others, and you'll be hearing from several people today who were similarly advised. And one of those is our very pleased to have with us is Andrew Nobel. He will be our first speaker. And he studied at Cornell in electrical engineering and Cambridge in mathematics. And he joined Stanford in the mid-'80s He got his PhD in 1992, advised both by Tom Cover and Amir Dimbo, who were two examples of that overlap of information theory and statistics and probability. He completed that in 92, went to University of Illinois, somewhat chasing me. That's a path I had taken. He was there as a postdoc. Had come here. And then in 1994, he joined the University of North Carolina, where he's had a very illustrious career. He is a distinguished professor of statistics, operations research, and biostatistics. And he is going to tell us about network comparison via optimal transport. Andrew.
Maybe I can just make a quick announcement. This is for all the speakers. So we have a system for helping timing. Okay, so we'll have flags. Could you wave a flag at 5 minutes before the end of the time, and then another flag at 1 minute, and then a red flag at the end of the talk time. But then there will be a couple of minutes for questions, after which another red flag will wave. Okay. And during those couple of minutes for questions, the next speaker, especially if you have a laptop to connect, you can come up and connect to that, and Andrew will be introducing the next speaker. Okay, thanks.
Thank you for being here, Andrew. It's lovely to be here. And I'm honored to be the first speaker, also rather nervous, so I apologize in advance if I'm stumbling over my words. I wanted to say a few things to start, and I think all of us here are indebted to Andrew intellectually in terms of, or in motivationally, and I'm no exception, and so I just wanted to thank Andrew here. Early in my career, when I was working with Tom Cover just after Andrew had left Stanford, the work that he had done there was still in the air, and my interest in thinking about studying stochastic processes and their relationships with statistical inference was inspired in large part by work that Andrew had done with Tom, and as I said, the kind of the zeitgeist, as it were, at Stanford at that time, including Bob Gray, Tom, and Amir, and other folks. So, Andrew, thank you. And also Andrew has, for me, been a great mentor and inspiration. We had many interesting conversations when he was back at Stanford to work with Tom, and I was still there as a student. So thank you. With that, let me begin the talk. So this is a talk about comparing networks and connections with work that Andrew has done and are perhaps not as direct as some other folks may talk about, but the key idea here is to think about processes. So, let's see, yes, whoops. Okay, so just by way of background, networks is data. Traditionally, which is to say in the past, networks were often the endpoints of statistical analysis. So this would be the way, once an experiment or a study was completed, that you might summarize your data or perhaps visualize it. And I think, as many of you know, right now networks have become objects of studies in and of themselves. So people are interested perhaps in clustering networks or finding relationships between a given set of networks. These questions are motivated by things like node level and graph level tasks. And I would say today, a lot of the methods out there are dominated by things like graphical neural networks and graph representation learning. What I'm going to talk about today is a slightly different approach, and it is, as I mentioned before, process-based. So the task we set ourselves was how to compare two potentially heterogeneous networks G and H, so networks that might not look the same. So the networks might be undirected or directed. They could be weighted or unweighted, and they might have vertex sets of different size. So we have two networks that a priori might not look like they are comparable. Nevertheless, we might want to see what things they have in common. broad goals would be some number that says how far apart this network is from this other one. So a numerical measure of difference. And then beyond that, we might like to align the nodes, the vertices, and the edges in the two networks and say, well, this vertex in this network is somehow associated with one or perhaps a set of vertices over here. So how to do that? So our approach, as I said here, is driven by some very simple stochastic ideas, and the idea is when you're trying to compare a network, it's a graphical structure, but we know that networks are in various ways associated with stochastic processes, and the simplest of which is just a random walk on that network. So our approach, and again, this is the talk right here, we convert each network into a random walk, right? That random walk is a Markov process. That's step one. Step two, we find a way to do some sort of optimal transport on those two processes. So that is pretty much the idea. The devil, as always, is in the details, and here the devil is mostly in that second bullet point, and that is what is the right way of applying optimal transport to these random walks. Okay, I'll say more about that in a moment. So I imagine that most of you have seen this, but let me just run through just some notation. So for us, a weighted network, we'll use G and H to denote weighted networks. We only need to consider two. We have a vertex at U, a set of edges. We'll consider the edges to be directed, and a weight function that assigns to every edge a non-negative weight. So our conventions are the weight function is going to be positive unless the edge is absent, in which case the weight function is 0. And for an undirected graph or undirected network, right, we have symmetry. The weight on this edge is the same thing as the weight on the edge coming back. The only definition beyond that I'll need now is just the notion of a degree or the out degree. So if I'm at a node, I just look at all the edges leaving that node and I add up their weights. That's the out degree. Okay. So how do I get from a network to a random walk? Nothing new here. We will consider what we've considered, and what I'll describe here is mostly the standard approach, and that is if I'm at a node, I look at all the edges leaving that node, and I choose an edge according, basically proportional to its weight, right? And then repeat. So it's that simple. Okay, so that's basically the standard random walk on a graph. And it will be helpful for us to only consider connected graphs, so that's going to be a restriction. But in that case, this probability transition matrix P yields a unique stationary Markov chain. So we have a Markov chain, it will have a unique stationary distribution if the graph is connected. And being connected just means that there's a path from any vertex to any other vertex. So in some recent work, we've called this a Markov embedding. So it's kind of analogous to if you embed a node in a network in Euclidean space. Here we are embedding the network itself in the space of Markov chains. But we'll drop that terminology here. But there are other ways of embedding or going from a network to a Markov chain. There's lazy random walks, non-backtracking random walks with random restarts. Okay, so but today we'll be primarily focusing on the first example here. Okay, now, at some point, right, there has to be a way of relating these two disparate objects to each other, and the way we're going to do that is through a cost function. So a cost function is just a function that takes a node in the first network and a node in the second network and gives me a non-negative number. Might be 0. But it's important that this is a vertex-based cost. There are more general things one can consider, but for starters, this is the most natural way to think about things. And so it's the cost function that is going to kind of help us link up the two networks. And if we're doing optimal transport, we know that we need a cost function. So here it is. All right. So what cost function do you need? So I've been asked this. So this is either you can think of this as an answer or a cop-out. Right? It's a cop-out if you have a specific practical question, right? Getting a cost function in a particular application, we have considered some applications, can be a very non-trivial task. But here are some cost functions that play well theoretically. The first one is the degree. So if I have a node U in one graph and a node V in another, I just look at their degrees, I look at the difference of the degrees, I square it, that gives me a cost function. If the two vertex sets are the same, so the graphs are different, but they have the same vertex set, then I can just use the 0, 1 cost. So very simple. More generally, if I've assigned a feature or a label to the vertices in both networks, then I can say that the two vertices are close if they have the same label, or I can use a distance or a metric on the label space. A special case of this would be if I've done some sort of embedding, so if the vertices of both networks have been embedded in a common Euclidean space, right, then the cost between two vertices can just be the Euclidean distance between their associated embeddings. Okay, so there's a raft of things you can use, and there are no particular conditions here determining what makes a good cost function or a bad one, but it will be application dependent. And admittedly, we can't, if you bring me an application, it might take 3 weeks of going back and forth to figure out what a good cost function might be, right? So, okay, so to kind of reiterate the theme, so here's the setting. We have two networks, G and H. Associated with G, I have a random walk X on its vertex set. Associated with H, I have a random walk X on its Y on its vertex set. And I have a cost function relating the vertices. And so our idea, as I stated before, is a simple one. Let's compare the networks by comparing the processes using the cost function. And to compare the processes, we're going to use an optimal transport distance. The obvious one doesn't work for reasons I'll mention in a moment, but if we restrict the set of couplings that we're considering, then we get something meaningful. Okay, so let's just start to recall what some basic definitions from optimal transport, just one that we need here. That is the notion of a coupling. So if I have two Markov chains, X and Y, these are processes, a coupling of those two chains is just, I'll write it as X twiddle, Y twiddle. It's a joint chain, so think it's a bunch of pairs, X0 twiddle, Y0 twiddle, X1 twiddle, Y1 twiddle, and so on. And the coupling constraint says that the X twiddles, if I look at them alone, have to have the same distribution as the X process. And the Y twiddles, if I look at them by themselves, they have to have the same distribution as the Y process. So that's a coupling. And so your first thought, the kind of naive way of applying optimal transport would be saying, well, I've got a cost function, and I have a notion of a coupling, so let's just minimize the expected cost overall couplings. Okay, and it's important here, a feature that emerges now is that when I'm taking the expected cost, it's at time 0. Okay, and I have processes, right, but I'm just looking, it's the marginal thing that's going to enter the cost. So, okay, this is a bad idea. The reason it's a bad idea is that there's a coupling of Markov chains defined here need not be Markov of any order, and it doesn't even have to be stationary, right? So if I can put two stationary chains in that are Markov and I get out something which is gobbledygook. And there's very simple examples I don't have time for, but you can write them down. So somehow thinking about all couplings probably too much. Right? And what happens, in fact, if you do this, then the only thing that really matters is the time 0 behavior of the chains, and you're ignoring the dynamics. So if there's the reason for looking at processes here, as I'll try to make clear later, is that if you couple the processes and you do it in the right way, then you are able to capture the dynamics of the processes. And if you capture the dynamics of the processes, you are capturing the topology of the networks, which is what you want. Right? So it's very important that even though, and I'll talk about this in a moment, but even though our objective function here is going to involve the time 0 behavior, if we are minimizing it over an appropriate constraint set, we do capture information about topology and dynamics. So that doesn't work. So we impose a condition, right? So we would at least hope, and this doesn't seem crazy, if I'm going to couple two Markov chains that are stationary, I should probably, right, look at couplings that are stationary and Markov. Right, minimally. So we go one step further, right, and we consider, and these are sometimes just called couplings of Markov chains. There doesn't seem to be good terminology in the literature, but we consider what we call a transition coupling. So a transition coupling is a stationary Markov chain, and so being a Markov chain, it has a transition matrix, and the transition matrix here, we're calling R, is maybe the clearest way to see it. Is there, right? So R is a transition coupling of P and Q. What does that mean? If I'm at, UV in my joint chain, right, then the transition to U prime V prime is that transition probability matrix is just a coupling of the transitions out of U and the transitions out of V. Okay? So that's all that's needed for this definition. The definition ensures that x twiddle, y twiddle is in fact a coupling. So, right, the x twiddle has the right distribution and the y twiddle does. Question? No? No? Okay. So it's a coupling. And so these are the objects that we're going to study. So this is kind of, for us, the right set of constraints when we're considering joint processes. All right. So there's an important fact here. It's not very hard to show. Provided we're considering irreducible chains, which we are, because we're assuming that our graphs are connected. So the stationary distribution of a transition coupling is a coupling of the stationary distributions of x and y. But the important part is not conversely. Okay, and we'll see why the not conversely is critical in a moment. Are there any questions about? I want to make sure I'm not going too fast. I don't see any flags, so I think I'm okay. All right. Okay, so here it is. So if I'm given two networks, and I find I guess I left this terminology, Markov embeddings. Just think of these are their associated random walks, and have a cost function. Then the first thing I can do is now I'll do optimal transport with respect to this restricted set of couplings, right? Transition couplings, and that gives me a number. Okay, so again, it's important to note here in both cases. So I've got this involves only the stationary distribution of these processes. Okay, so we have a cost function that looks like it's somehow one-dimensional, but I have a constraint set which is sort of infinite dimensional, right? So here's what we're not doing, right? We are not trying to minimize the expected cost over the set of stationary distributions of our couplings. Sorry, over all stationary distributions. We are minimizing the expected cost over the stationary distributions of the transition couplings, which is not all couplings. And in fact, it's not a nice set of couplings, right? So even though there's convexity floating around when we project from the transition couplings down to their stationary distributions, that set is not nicely behaved. But that's exactly the set that we want to minimize over. And if we didn't do that, it wouldn't work. I mean, it wouldn't be very useful. So, all right. Maybe it's this particular problem, but I actually don't think that the network distance is very interesting. I think it's not the min that's interesting, it's the argmin, right? Because the argmin here, the optimal transport plan, gives us a ton of information, as I'll describe, right? And from a more practical point of view, I think it's where the action is. So, a couple technical things. The minimum exists, right? That's just a compactness argument. And it may not be unique, right? So you may call into question any interpretation I try to give after this. Well, if there's three minima, which one do we use? I do not have a good answer. So mea culpa. And importantly, the minimization is carried out analytically. We are not randomizing, and something that makes me especially happy, there's no free parameters, right? So this is a completely deterministic problem. I'm not hiding anything. There's no need to tweak something or approximate something. It's all done as you see here. All right. Let me say something about computation. 150 nodes, 200 nodes, then it gets slow, right? So this is a real practical limitation. We've actually applied this to some neuroscience problems where we are dealing with things that have 150 to 200 nodes. But if you bring me two networks with 1,000 nodes, right now I don't know what to do. So just to be like truth in advertising. Okay, if we could handle 1,000 nodes, I'd be thrilled. We're actually trying to find better ways of doing the computation, but for now, this is a little bit limited in terms of what we can deal with. All right, in any case, maybe a useful fact, if U and V are the same and C is a metric, then the network distance is a metric. So just kind of nice to know. All right, so what are the important deliverables of this approach? Right? So as I said before, they really flow from the optimal transport plan itself. So if you think about what the optimal transport plan is, it's a random walk, right, on the tensor product of the two graphs. right? So we take two random walks and we're sort of linking them together. I have a linked random walk, right? So that random walk has to have the property that if I just look at the x's, they do the right thing. If I look at the y's, they do the right thing, right? But what the coupling does, right, is it's trying to keep the XY pairs, right, the process to favor pairs that have low cost. Okay? So that's effectively what's going on. So when we have the optimal transport plan in hand, then we can use it easily, say, to define a kind of vertex alignment, right? Now, it's a soft vertex alignment. It's a probability, so the pi sub v just means pi is for alignment, v is for vertices. So pi v of uv is just the probability that, right, at time 0 or any time you want, because the process is stationary, right, that we're in the state uv. So that gives me a way of aligning any vertex in G with any vertex in H. And more importantly, and this is for us, I should emphasize that of the methods that we're familiar with for graph alignment and comparison, none of them do this natively. And because you're looking at a process, right, you can actually align edges as well, right? So how do you do that? Well, the alignment, if I want to align an edge UU prime over here and an edge VV prime over here, it's just this probability on the right. Okay, so we can read that off immediately from the argmin. Thank you. Okay, another important property of this is that the optimal plan is edge preserving, so we don't create edges that aren't there. Right? So if we align two edges with positive probability, the edges actually have to be in the given graphs. And all these properties flow from the definition of the transition coupling. Okay, so let me just give a couple of examples in the few minutes I have left. So here are 3 graphs. Each of them have 8 nodes, and I've embedded them in the unit square. So G1 is a circle, or cycle, right? G2 looks like G1, but I've removed an edge, and then there's G3. So the question is, which of these is closer to G2? Is it G1 or G3? And of course, there's no, it's not a right answer, right? But the question is, what does your method prefer, right? So if you're looking at topology, then you put G2 with G3. If you're just looking at how these things are, and so remember, our cost function is Euclidean distance, right? You're just looking at cost, right? You would put G2 with G1. So NetOTC says, in spite of the fact that the costs don't quite match up, because of the topological difference, right, G2 is closer to G3. Other methods here, if you just try to match up the marginal distributions of the processes, and this is one of our competitors, FGW, it's a good method, so I'm not here to bash it. It's a great method. Please use it, right? That they put G1 and G2 closer together. Okay? There's not a right or a wrong, but this is just to point out a critical property. Let's see. It's this. I'll skip over. This is we applied our method in some competitors to some network classification tasks, and it did fine. Right? It was competitive. Sometimes it won. Sometimes it didn't win. Yeah. All right. Okay. More important, isomorphism. So here's a simple graph, and we created an isomorphic copy by just permuting the node labels. And so the question is, can we recover, if this is my G and my H, can I actually recover the isomorphism, right, by applying a transport-based method? So we applied alignment methods, several of them, with this degree-based cost function. And then when we were done, we paired each U and G with the V and H that maximized the joint probability. Okay? Now, degree-based cost doesn't seem like a good choice for this, because everybody has degree 2, right, except for the thing where the stick hits the popsicle part and the end of the stick, right? So if you're not accounting for topology, right, which is to say if you're not looking at the process, you're hosed. So here's what happens. So this is if you just look at, you couple stationary distributions, then basically the topology doesn't matter, and you can send anything of degree 2 to something else of degree 2, and you get a kind of random assignment. This is our competitor, and if you look carefully, it's not perfect, right? There's some things that are kind of misaligned. And of course, I'm showing you this because we win. Yay. All right, and we tried some other examples, and we did well there too. So the point is the degree-based cost is not informative, but again, we're coupling processes, we're not coupling stationary distributions. Sorry if I've said that 8 times, but that's the key idea. All right, let me give you one theoretical result to close. So and this is ongoing work. So let's consider using NetOTC with this degree-based cost that I've mentioned. Then you can show that if for the family of trees, right, I'll read off the statement, right? So if we have undirected trees, G and H, right, then their network distance is 0 if and only if they're isomorphic, right? So we're able to completely capture isomorphism, right, through this network-based distance, right, for trees. We can't make the same claim we'd love to make the same claim for other graphs. Now, by the way, you might ask, the computation of the cost is not polynomial time, so we haven't, this is not Fields Medal-worthy stuff here, right? So we're just saying that, right, that for this family, right, we can, the isomorphism coincides with cost 0. And there are other families for which we can make similar statements, but we're kind of working on that. All right. So to summarize, very simple idea. As I said, the devil's in the details, but here's the idea again. We can regard given networks as random walks in different ways, and apply constrained optimal transport to compare the random walks. And as I said, deliverables include ability to compare networks of different types and sizes in the soft alignments of nodes and edges. So, let me acknowledge and thank my collaborators and financial support. Thank you very much.
One or two questions? Oliver?
So you described an optimal transport plan that gets you from one graph to another. Oh, sorry. You've described an optimal transport plan that gets you from one graph to another. Does it also come with any sense of a geodesic? Can you tell me what the graph is halfway between those two graphs?
That is a great question. And that is, I think you could probably try to extract some type of geodesic but you would be looking essentially at, you would take that, you would probably want to start with, let's say, the product, right? One transition coupling is just to look at P and Q and multiply them together. So one can imagine, I think, a geodesic going from the product, right, which is probably not going to be optimal to the optimal plan, right? But I'm not sure if that's not exactly going from one, that's going from one coupling to another coupling. In terms of going from one graph to another, I'm not sure, but it's a great question.
Thanks.
So an interesting coupling, here you're coupling by joint distributions. Yep. We can be curious, when does the optimal joint distribution make the distribution of V given U or U given V deterministic? Do you have a handle on that?
Yes, so thank you. That was kind of like, I'll rate you a check. So we have a whole bunch of stuff on factors, right? So when you think about graphs this way, right, there's a very natural way to think of one graph as being a factor of another if basically its Markov chain is a function, right, of the Markov chain associated with the other graph. And weirdly, this notion of factor does not seem to be well explored in the graph theory literature, in which there are many definitions of factors. So there is a formal definition of factor, and you can, if anyone is familiar with joinings in ergodic theory, there are ways of understanding factors of graphs and Markov chains in this way that tie in with some things that people have studied in ergodic theory. Now, practical implications of those right now, one reason I didn't mention is I don't think we have many, but there is some theoretical stuff one can say.
Thank you, Andrew.